Notice that we have a 3x3 kernel, but in our case, our first convolution has a 6x6 kernel. So the question arises of how do we handle even size filters? We know that odd size filters have the kernel as the receptive field, but in even size filters, how do we handle that? And the answer is pretty much in the same way, as you can see in this example from Peter Bielewski, NVIDIA PyTorch lead. And we're basically going to run this in our Colab environment. So let's jump here to even size filter section, and let's run this. And here, what we're saying is if we have an input tensor of 4x4, ranging between 0 and 15, and then we have a 2x2 filter or kernel, then if we have a stride of 1 and padding of 0, we'll get an output tensor of 3x3. So let me show you this in a more graphical way. So here we have our 4x4 input tensor that is convoluted with a 2x2 filter to obtain this 3x3 output tensor. So given that we're using a stride of 1 and padding of 0, what will happen is the filter will first be applied here on the top left, and then we will be performing element-wise multiplication between the values here and the kernel. So in this case, in order to obtain value 10, we've multiplied 1 times 0 plus 1 times 1 plus 1 times 4 plus 1 times 5. In this case, we're aggregating all these values into 10 because of the matrix. You could have different filter types, as we saw earlier with the Prewitt, Sobel, and the Laplacian filter. And of course, this one is actually very small. But the same fundamental operation happens with larger tensors and larger filters. So what's going to happen is that the kernel is going to be convoluted for this part of the image. And then given that we have a stride of 1, we're going to move 1 pixel to the right and then perform that operation. And then 1 more to the right and then perform that operation. And we cannot go any further because the whole kernel has to be within the image. So that's why we have 3 of width. And then similarly, for the height, we will start right here and we're going 1 down because we have a stride of 1. This is often referred as 1, 1 to show that it is in both dimensions. And padding could also be shown as a tuple of 0 by 0 to show that you're adding 0 padding here, 0 here, 0 here, and 0 here. And padding actually could be even shown like this. In our case, if we only provide one value, that means that that's applied for the different dimensions. So we can just simply show it like this, and then 1 to the right, 1 to the right. And then similarly, we're going to perform this operation, 1 to the right and 1 to the right. And that gives us this 3x3 output tensor. Now, similarly, if instead of stride of 1 and padding of 0, we have a stride of 1 and padding of 1 with the same input tensor and the same weights, the same kernel, the output in this case would be a 5x5 output tensor. And we can actually see that here as well. So in this case, we have the same input image, but we are adding padding 1 across all the dimensions. And usually padding consists of zeros, but you can pad different values if you like. But for example, the conv2d function from PyTorch defaults to 0, but you can change it for your use case. In this case, we add in across all borders and we have the same kernel. So in this case, what will happen is that instead of starting here as before, now we start after the image has been padded. So in this case, we will start right here and perform that operation, which you can see here as well, basically 1 times 0 across all of them. So it's going to be 0. In this case, it's going to be 1 times 0, but one of them, this one right here, will be multiplied by 1, and that gives you the result right here. So before we had a 3x3, now we're going to have a 5x5, and showing you how that happens is, again, in a similar fashion. We start here, we just go 1 to the right until the last operation where we can completely fit the kernel inside the image. So we cannot do this because part of the kernel is outside. So that's why this is the last operation here on this row. And then similarly, we perform the operation right here and keep moving 1 to the right until we perform the 5 operations that we can perform. And then we'll continue through the different columns until all these operations have been performed. And the last one will be here and here. That will be the last one. So in this case, again, by adding padding, now we obtain this matrix, which corresponds to the matrix that we obtained right here in Pierre's example. Now, if we want to take this one step further, we could focus on this here, where we have a 10 by 10 input tensor. Here, we're just expanding the dimensions so that they're the same dimensions so that the convolution operation can be performed. But this is a 6 by 6 kernel that is going to be convoluted by a 10 by 10 input tensor. So if we run that, the result would be a 5 by 5 output tensor. And we want to do that so that we're not just having a stride of 1. In this case, we have a stride of 2. And similarly, now we have padding of 2 instead of 1. So we're just taking Pierre's example to see how it generalizes to other strides and padding. So let's see this visually here. So let me jump to this tab. And again, we have this 10 by 10 tensor with padding of 2 across every border. And then this 12 by 12 tensor now is going to be convoluted by a 6 by 6 kernel. By the way, this padding is performed behind the scenes by PyTorch conv2d function. You usually just feed in the input tensor and then indicate the padding and the stride. And then before the convolution is performed, internally, PyTorch is adding the padding for you. So in this case, this convolution will result in a 5 by 5 tensor. We will apply this 6 by 6 kernel, and the first one will be, as always, on the top left of the image. So you will have one output result, which will be stored right here. And then similarly, now the stride, instead of going 1 to the right, we're going to go 2 to the right to here. So the next operation would be this one. And then similarly, we go 2 to the right. This is the next operation. And again, 2 more to the right and this operation. And the last one that we can actually perform is this one, where the whole kernel fits within the image. That's why you have 5 values here on the output. And vertically, given that the image is square, you also have 5. And before we started here, now you go 2 pixels down, since we have a stride of 2 across every dimension, and this will be the operation, and then this is the next one, and so forth. And then similarly, for this one, and then 2 pixels lower, and you can see that this is the last one that we can actually perform on the vertical dimension. So we'll perform these operations right here to obtain these final tensor values. And this is the last one where we actually obtain this corner value right here when we perform this element-wise multiplication between the padded tensor and the kernel. And by the way, this Google spreadsheet will be available in the video description. Now, one last thing before we wrap up this video. So if we go back to the initial example where we had a 4x4 input tensor and a 2x2 kernel, well, in this case, I changed the values from all 1 to 1 to 4. And I did that to show the difference between two methods. When we run the conv2d from PyTorch, technically we're performing cross-correlation. And if we go to the PyTorch documentation, you can actually see here as well, where we're performing cross-correlation. This operation is just generally referred as convolution, but technically, especially if you see it in math textbooks, you'll notice that cross-correlation is what we're actually performing, where the kernel is element-wise multiplied without any rotation. Technically, the convolution operation requires a rotation of the kernel before applying this operation. So in this case, I rotated this kernel 180 and then rewrote it here. And technically, this is the convolution operation, where same operation is just that the kernel gets rotated. Given that the kernel values are rotated 180, then the results of the output tensor will be also different. So you don't have to worry about it much, but just for your awareness, if you hear the term cross-correlation, this is actually what we're performing when we call the conv2d function.